Hello students, welcome to EduCell. In this video, we are going to discuss about one of the hard reductions, which is Hamiltonian cycle reducible to TSP or traveling salesperson or salesman problem. Okay, so what exactly the Hamiltonian cycle? What is traveling salesman problem or traveling salesperson problem? That will be going in detail. But as for the video, whichever I have already uploaded for the easy reductions, please watch that one if you are new for this hard reductions. Why? Because certain reductions we have done, which is like we are reducing the complexities, or else we are just keeping the same time complexities, but we are not enhancing that one. Because reduction, what exactly we are using reduction, that I have already told you in the introduction video. Like we are reducing the problem, main reason is to reduce the time complexity. If it is huge, like you can say exponential we are getting, we can, if it is reduced to at least some polynomial, we can say reduction is good for us. Okay, reduction means we are completing a problem, like we are trying to give a solution to a problem using another or existing or a known problem. Okay, so the right hand side here, as per the example, like as per the problem which we have selected, traveling salesman problem is known to us. Using the traveling salesman problem or a salesperson problem, we are trying to give the solution for Hamiltonian cycle. This is what it is written. Okay, so now we should know what is Hamiltonian path, what is Hamiltonian cycle or circuit, or Hamiltonian graph. Okay, so I've kept just the definitions here. This is for the Hamiltonian path. So the definition, it is written like whenever we are finding the Hamiltonian path, you should keep in mind, if you start from any of the node or any of the vertices, the starting point will not repeat. You can cover all the vertices, but the edge should not repeat, as well as the vertex where you started, that should not be repeated. It is written like, if there exists a walk, okay, means we started it in the connected graph that exists, every vertex of the graph exactly once. Okay, we will cover all the vertices exactly once, but repeat is not possible. Okay, exactly once without repeating the edges, then such a work called as Hamiltonian path. Okay, like we will be completing and we will not repeat that one. I'll give you the example, and note is written like in Hamiltonian path, all the edges may or may not be covered. Okay, but edges must not repeat. Okay, or else you can say the vertex also not repeat. I have to actually write that one. Edges and vertices, edges, like you can take an example here. I'm just giving this example. The for this one is A for us, or might be here. If we start our walk towards B or towards D, there are two directions. If you start, if you pick A, okay, if you go towards B, now we covered it. From B only one direction is there, C. Okay, now from C there are two directions, either you can go towards D or you can go towards E. If you go towards D, clear. Next, I told you we will not repeat. If we are going to repeat it, this is not a Hamiltonian path for us. Clear? So we will just not repeating the edges as well as not repeating the vertices. So the Hamiltonian path could be written as A, B, C, D, E. If you are going towards this direction. Okay? Clear? If you are taking the other directions, like you came here up to this, now you are picking this instead of that, C to D. Instead of C to D, you are keeping C to E. Okay. Next, from E to D, here as per the Hamiltonian path, what exactly it is written, we have to cover all the vertices. Okay, all the vertices will be covered, but the edge should be covered one time, or edge should be selected for the one time. Okay, or right, the vertex should be covered for the one time. So in this way, if you are completing this path, the Hamiltonian path HP will be written as, Hamiltonian path will be written as A, B, C, E, D. Okay. So more than one Hamiltonian path could be possible in a graph. There should not be only one Hamiltonian path or one Hamiltonian cycle, or anything is not exactly one. might be more than one could be possible. I have given the example here. Okay, so for the another one, for the other graph, we should have to have a look here. If you start from E, okay, here we can move either also towards D also we can move. If I'm going towards this one, B, then C, then D, then A. If I'm doing this one, if I'm doing this A, B, C, D, then again A, there will be a problem. Okay, why? Because a repetition of vertices should not be allowed in Hamiltonian path. So the Hamiltonian path could be like E, A, B, C and D. Clear? Or else what you can do in other way also, E, A, D, C, B. Okay, this is also a Hamiltonian path, could be written or rewritten as this one. Okay, so there are, we found two Hamiltonian paths, but this is not always to get only two Hamiltonian paths. There might be more than one, might be 5, might be 7. It depends on the graph. Okay, so here if I'll take this example to find the Hamiltonian path, if I start from F, maximum students have the problem like, why should we start from this A, E, F? Can we start from B? Yes, of course, not an issue. If you can start the same example I'm just saying, okay, you can start from B, clear, then B are stuck at A, clear. Suppose B towards A, here we stopped at E. So this is Hamiltonian path also, but the problem is whether if exists a work connected the graph that visits every vertex, whether it is uh, like covering the vertex, all the vertex, yes or no? Definitely it is no, no, because you started from B to A, then only one we can reach, but repetition is not allowed. Clear? So that's why we cannot say from this direction. Yes, if you can pick from B to C, then B to D, then D to A, then D to E, A to E. Clear? So if such path you are writing, so the Hamiltonian path could be written as, okay, this is the Hamiltonian path. Clear? So you can start from any of the vertices. Nobody says like you should start from A, you should start from 1. No, nothing. You can start from C, you can start from D, you can start from E, anywhere. But as for the example, in general, uh, the faculty members are just starting from the first one. Okay, this is not always true. Clear? You can start from F. I'm just starting from F, suppose. So I have two paths. Clear? I can do this one. Then I have to come towards C because the by default one. From C, I have to go at least towards D or towards E. Clear? If I'm going towards D, I cannot go back to E because repetition is not allowed it. If repetition is not allowed, we cannot exactly cover all the vertices here. So Hamiltonian path could not be established if you can start from F. You just think, no, why not we start from C? Just for example. Okay, not an issue. You can start from C towards D. You can go towards A, or might be you will be stuck somewhere. Means you cannot cover all the vertices from this graph. Okay, from this graph we cannot expect any Hamiltonian path could be established. Why? Because if you can start from B also, towards A we can move, but if you go top we will be stopped. If you go down, not an issue, you can come here, we can come here, we can come. But what about the F? There is a problem. Clear? So Hamiltonian path is not possible in this case. I hope it is understood by you. Clear? Next, to the Hamiltonian circuit and cycle, both are same. Like how to differentiate then? A Hamiltonian path which starts and end at the same vertex. Okay, means you started from A, suppose you will come towards A again. This is what you can say, it's a Hamiltonian circuit or a cycle. Okay, clear? So as I told you, the repetition of vertices is not allowed, but here repetition of vertices is allowed. In which case, like the start and end should be same. Okay, if you start from suppose A to B, then C, then E, then D, then A, definitely we can say A, B, C, E, D, or else you can write A also because we are completing towards A. So we can say it is Hamiltonian cycle or circuit for us? Some of you have also a question, okay, like the when can we say this one is a Hamiltonian cycle for us? If you can go for it. So here the Hamiltonian cycle could be written as A, B, C, D, A. Clear? But one more thing you should remember, a Hamiltonian path which starts and ends at, okay, the same vortex. It is written. Okay, that's why we are saying the Hamiltonian path if we are having a Hamiltonian circuit. Clear? We are having Hamiltonian circuit. If you just remove any of the edges, that will convert to Hamiltonian path. If you say this one means ABCD, if you remove any of this, suppose A to B is getting removed, can it be Hamiltonian path? No. Why? Because E is not present there. Okay. So that's why I told you like it should be cover all the vertices. Clear? Next is Hamiltonian graph. How do we say? Clear? If it is Hamiltonian cycle for us, like we started suppose from A to B, clear? From A to B, then B to C, then C to E, next from E to D, next from D to A. This is what a Hamiltonian cycle is. To represent that, I have written here, during construction of Hamiltonian graph, we should keep or we must keep the used vertices as well as the edges which are responsible for making the Hamiltonian cycle. This only these edges are responsible. So how to make the Hamiltonian graph then? This is how we can make the Hamiltonian graph. Okay. This is what the Hamiltonian graph HG. Okay, Hamiltonian graph will be written in this way. Like using these vertices as well as these edges, we are getting the Hamiltonian cycle or a circuit. That's what we should represent that one. If we are representing that one only, the responsible edges and vertices, we are writing or we are renaming or we are naming that one as Hamiltonian graph. Okay, so I hope it is clear to you. If any doubt, you definitely comment below and I'll definitely answer to you. And here how we can say it's a Hamiltonian cycle. For this, whether we can get a Hamiltonian cycle or not, we just want to check it out. You can go to check it out, like from E you can start a not an issue. From then yes, yes, yes also. But D to A, when we are repeating, up to this it is okay, but can we go back? Never. Why? Because repetition is not allowed. Clear? Only repetition where we are allowing only the vertex where we start. Here we started from E and we ended with A, and repetition is not allowed. Though repetition is not allowed, we are not able to reach to E. That's why it is impossible to find a Hamiltonian circuit or cycle in this graph. Okay, also for the same one, like we can start from F, you can start from any one, but I just started with the F, then B, then C. Here a problem, though it's not Hamiltonian path is not possible, definitely Hamiltonian cycle is not possible. If Hamiltonian cycle or circuit is not possible, definitely Hamiltonian graph is not also possible. Here Hamiltonian path is possible, not an issue. That's why we are trying for the Hamiltonian cycle or circuit where it is not possible. If Hamiltonian circuit or cycle is not possible, that's why HG or Hamiltonian graph is also not possible. In this case, Hamiltonian path is possible, Hamiltonian circuit or cycle is also possible, Hamiltonian graph is also possible. In this order only. Clear? If you started from A. If you just think you start from B, B to C, then E, then D, then A also it is possible. So these responsible edges and the vertices will be responsible to make or construct this Hamiltonian graph. Okay. I hope it is understood by you. Clear? Then we should know what is traveling salesperson problem or traveling salesman problem. Okay, so as per the definition, it is written, given a list of cities. Okay, I think like traveling salesman means, let us take an example of an Amazon delivery boy, or might be a Zomato or Swiggy delivery boy, or might be those who are delivering the products or parcels. Okay, even if Ola is introducing the parcels, so whatever the parcels is getting to be delivered, so at that time what exactly we should have to think, let us think there are different locations. Here, as per the definition, I just kept only the cities. Okay, so this information I have collected, this particular definition I have collected from the Wikipedia. You can visit that one also. The detail is written there. So given list of cities, okay, you have a list of cities as well as the distance between each pair of cities, okay, that will be given, means weighted interval or weighted, you can say weight is assigned to all the edges. This is what exactly it's written. Okay, so what is the shortest possible route that visit each city exactly once and return to the original city? Okay, like where you started, okay, there you may visit, not an issue, but the distance you should cover is minimum, as well as you will return to the original city also, that will be considered. The whole what exactly tells, the covering should be minimum. Why? Because in general, in a real life scenario, what exactly the traveling persons are doing, they are trying to optimizing the petrol. The main reason is optimizing the petrol. They are trying to find the shortest route. Otherwise, as well as the time also there, okay, they have to deliver it within time, as well as the petrol should be or might be the vehicle which are like, if they are using EV vehicles also, the charging they have done might for one day, that should be within this range. Okay, definitely we are working for the in real life we are working for the natural resources. Okay, but in algorithm we are working for optimization of artificial resources like time and space. This is what I told you repeatedly in other videos too. Clear? So exactly a traveling salesman problem tells us whatever the covering we are doing for each the cities, we should cover it once and we should come back to the city where we started our journey, or might be the origin city. We should come back, but the distance which we covered or might the salesman covered, that should be minimum one. Clear? This is what the traveling salesman problem is. So it is written in this way. Let us take an example. As I have given you the example in Hamiltonian path or Hamiltonian cycle, the same example, slight different, I'm just running it because your weight should be there. Okay, without which we cannot say whether it is minimum or not. How do you say if there is no such distance given? So you might uh, if you start from A, you can go towards B, you can go towards D as per the example, but it's not always true now. There should be an age, there should be weighted age. Okay, unweighted age we should have to avoid. Clear? So let us start with this. Suppose these are the weight assigned. Here this is 1 and this is 1. Okay, B to D is 1, A to C is 1. In general, in the exam, what type of question you can expect? Such graph will not be provided. Only with the vertex, the edges are to be mentioned. Like A, B, A comma B, the values are like 1. Like this, they can mention it. So indirectly, the graph, by providing the graph, they are just writing in a B manner or might be a vertex manner. Okay, so suppose think you might have a question. Okay, our target is in traveling salesman. We can cover all the vertices, no doubt, and the origin should have to reach the origin. Okay, so can it be possible only one traveling like TSP, only one TSP within a graph is possible, or more than one? I must say for this answer, more than one TSP could be possible. As we have seen, more than one Hamiltonian path or more than one Hamiltonian cycle could be possible. For this, the graph case also the same there. So here, what exactly you have to do, you just remember, like if you can start from A, I'm just changing the color. You can start from A, then B, then D, then A. Okay, for this, A to B, then C, then D, then A. You can write A or you can omit A at the end. Okay, I'm just writing it for to give you the proper example, like how we are getting it. The distance which we covered, we should write it. Okay, the distance we covered here is 10. Okay, so I'm just adding those one. Like our target is we should cover all the vertices once. We will cover all the vertices once, but the target is the distance should be minimum. Clear? Now I'm just changing the color and I'm trying to find whether any other possible, because this is undirectional. If undirected edge is given, so definitely both direction, means if it is undirected, that represents both the way we can move. Okay, but here as per the problem we should go in a single direction, but repetition is not possible. So you just think like A to C we can also move. Okay, but C to A is not moved by us, because as per the problem, though it is bidirectional, but repetition is not optional. Okay, so now you just think like we can start from A to C, then from C to B, from B to D, then from D to A. For that I'm just writing A, C, then B, then D, then A. The distance would be like 1 plus 2 plus 1 plus 4. So definitely we are getting as 8, which is a minimum one. Clear? If we start from A, there are two different paths could be established or might be found out. From this, we can get this value as the minimum value for us or optimized value for us, which is a TSP problem represents as this one. Clear? So I hope it is clear to you what is TSP. This one is considered as a TSP, but this is not providing us a minimum one. Okay, minimum we are not getting. Minimum we are getting from this path. That's why we are picking this as TSP. Okay, this is our TSP for us. Why? Because minimum we are getting out of this two. Clear? So as for the complexity, we should decide. Using dynamic programming, the complexity we can expect is 2 to the power n into n to the power 2. Means is a product of polynomial as well as the exponential. Okay, this is the time complexity for TSP. For the time complexity here, we can expect as n factorial. Okay, which is less than n to the power n. Sometimes some are saying the factorial is equivalent to the super polynomial, but I must say it is less than n to the power n, but definitely the upper bound is n factorial. This is the time complexity here. Clear? So what exactly we are doing? As per our problem, we know traveling salesperson. Using traveling salesman problem or traveling salesperson problem, we are finding the Hamiltonian cycle. Okay, for that problem is given. We try to find out a Hamiltonian cycle or a circuit. Okay, an unweighted graph is given to us. Okay, as an input. Next, output. What exactly the output we should expect? Does there exist a simple tour that visits each vertex of G without repetition? Without repetition. Whether there is an existing of this thing or not. Okay, though it is a decision problem for us. So Hamiltonian cycle we are finding out. Clear? Hamiltonian cycle, as we have already told, like we have seen there. So Hamiltonian cycle means we have to repeat, we have to visit all the vertices. Clear? That should be once. Means without repetition. It should be our output. Then for that algorithm, G is a graph that we can representing. When we are representing the graph, we are representing in this way. V represent the vertex, E represents the edge. Okay, this is our vertex. This is our edge. Next, construct a complete weighted graph named as G dash. Okay, that will be V dash or E dash as a vertex and edges. Where V dash is like we have shifted all the vertices to there. Okay, this is how we are writing it. Next, N we are introducing, which is all vertex. Whenever we are writing V in this order, whenever we are writing this, so the number of vertices will be shifted to N. This is how we are representing it. I'm just writing an example. Here we should start from 1 to n. I'll tell you like here 1 to n it is written. Better we should name it from 1 to n. Okay, 1, 2, 3, then 4, 5. Suppose this is given. Okay, this is given. Though it is unweighted. Okay, unweighted, not an issue. Whenever we are writing, so here this graph to another graph we are actually moving. So for that, what exactly we are writing? 2. This is our G. This is our G dash. Whenever we are writing G dash, so edges and vertices we should have to write, and the vertices V dash should be V, means the number of V which we are creating should be similar here. 3, then 4, then 5. Okay. Next thing is n here is written in this order, means 1, 2, 3, 4, 5. So n will be 5. The number of vertices will be represented as, like the number of vertices will be shifted, like how many number of vertices are there, it will be n. Okay. Next, for I to n we have to run a loop. As for j, we have to also find a loop. Why exactly we are doing? Because we are giving a weight, where we are assigning the weight. Okay, because it was previously unweighted, so we are giving that value. So this is representing unweighted, unweighted to weighted. Unweighted to weighted we are converting. That's why we are writing this one. Why? Because I told you the traveling salesperson must work if there should be the weight assigned, otherwise it will not run. So in this order, like 1, as per the for loop, so we can start from 1, then within that, if it is completing with n, then we shifted with I plus plus. Okay, so we start from 1, we have to check 1 to 2, like here 1 to 1 is not possible, then the inner for loop will be enhanced to one more time, like for 1 to 2, here we have to check weight of, like if I and j belongs to the e, then only we will assign, otherwise we will not assign. It is written in this way. Okay, like within that, like for I is equal to 1 and j is equal to 1, suppose. So then 1 comma 1, 1 comma 1, okay, belongs to E, means the set of edge or not. 1 to 1 means a self loop is existing or not. No. From the given graph, like we are going to reduce it. So whenever we are going to reduce it, it is not possible to have this self loop. The self loop is not possible. We must say, if you can add it and you can name it as, because else part it is written, we should name that was as 2. Okay, otherwise we can keep as it is. Okay, so you just think, no, I should add, you can add and you give this value as 2. Okay, if you're giving the value as 2 and the lowest value will be picked, that's why either you can ignore that one or you can make that one. Okay, next j value will be incremented, because once we'll complete from 1 to n, then only we can switch towards the I value. Okay, now j value is converted to 2. Here we have to check whether 1 to 2 set of edge is existing or not. Yes, it is existing, so you can keep the value or you can update the value as 1. Okay, it is written, else the value would be changed. Here the value will be converted to 3, means I1 comma 3, whether there is an existing edge or not. No. If you want to say, no sir, I have to use that one, okay, I have to use that one, you can go, not an issue. If you can go towards this now, what will happen, do you know? So you have to write this as 2. Clear? So 2 means you will not never pick that one in future, because the lowest one will be picked, but you can ignore that one, not an issue. Okay, so in this order, like 1 to 4, I'm just running for at least one time, you can get it. Like 1 to 4, there is no such age present, so we will not update that one. Now 1 to 5, whether 1 to 5 any age is existing, yes, so you put the value, you update the value as 1. In this order, you can again the I value, once it is completed, now I value is updated as 2, then we started from 1 to n again, because this is a loop with the inner loop, where depending on inner loop, the upper loop or the outer loop will work. Okay, so in this order, what we'll do, sir, in this order, clear now? We'll get, I've just kept an example there also, the same example with little bit changes I have done. Here I have just mentioned one. So you think, if you can run, okay, you can do that one also, or else you can do that one also, as we completed with this program. so we should keep that one. Okay, next what we have to do, this inner loop is ended. Now traveling salesperson decision problem we should run. This g dash with n means g dash 5 means the number of vertices are 5. We have to run this one, means we should have to find a path. Okay, I'm just changing the color. If you can start from 1, then 2, then 3, then 4, then 5, then 1, because this is what our traveling salesperson is. We will collect all the vertices. As per these vertices, we will try to complete this. So the vertices, if you can count, are 1, then 2, then 3, 4, and 5. 1 also you can write. This is our TSP. Okay, this is our TSP. The terms and condition we have actually mentioned here as 1. We kept all the vertices as all the edges as 1. So we kept, that's why we can find it out. And this TSP is equivalent to or equal to the Hamiltonian cycle. You just check now. This is our Hamiltonian cycle could be possible because we started from one end. So as I started from 1, so I'm ended with that one. If you can start from 2, 3, 4, 5, then 2 also you can end it with this one. If you can start from 3, you can come towards the 3 also. But repetition is not possible. Only one repetition we are actually allowing for the same vertex where you started. Okay, the TSP is saying that one. This is how you can understood. And I'm just saying here also you can start from 1 to 2, then 3, then 4 to 3 to 5. So it should be 4, or might be here you should can keep as this one. So here 1, 2, 3, 5, 4, or 1 you can write. These are our TSP. This is also our Hamiltonian cycle or a circuit for us. Okay, so now we should find out the complexity. Okay, for this complexity, this is just we are constructing. Once we are constructing, so it is big of 1, it is big of 1, we are just constructing that one. For this, the inner loop we are using 2 inner loops, it is n square, and traveling salespersons, as I told you, it is n to the power n using dynamic programming. So the total complexity we can expect is like the upper bound, n square is less than 2 to the power n into n square. So that's why we are saying the complexity is getting reduced to this one. Okay, instead of, I'm just writing, instead of getting n factorial, we are getting the result as this one using TSP. Using TSP, the time complexity of Hamiltonian cycle is big of 2 to the power n into n square. Okay, which is less than the n factorial. I hope this is clear to you. If any doubt you will be having, please comment below. Thank you. Have a good day.